When at all possible, a graph should be drawn to help visualize the relationship between the variables in our experiments. Anytime we graph our data, not only can we describe the relationship verbally, but we also need to write a mathematical equation to describe that line. Most of our data in this class will end up with a linear relationship between the variables. This is really good for us because we have the math background to be able to describe this type of relationship. Remember algebra? When your graph turns out to be a linear relationship, you can use the slope form equation to describe the data. This is an extremely useful equation, but is also extremely general in its initial form. The x and y in this general equation represent variables. X and y are general variables we use when we don't really know what we are talking about. When we graph data from a lab, we know exactly what the variables are that we measured. In the Comparing Volumes lab, we compared the size of a milliliter to the size of a cubic centimeter. Our independent variable, volume in milliliters, was graphed on the x-axis. This will make it our x variable in our equation. So instead of using x in our equation, we will write volume in milliliters in its place. Similarly, our dependent variable was the volume in cubic centimeters. This was graphed on the y-axis, and so the volume in cubic centimeters can be substituted in for the y variable in our equation. Now keep in mind different graphs will have different variables, so it is important to pay attention to what is actually graphed on the x and y axes. One really great thing about using Logger Pro is that when you do a curve fit of any kind, it gives you quite a bit of information about the line on your graph. For our equation, we are interested in the slope and the y-intercept. Again, m and b are very general representations that we use when we do not know the values for the slope and y-intercept. Once we graph our data, we have that information, whether Logger Pro gives it to us or we figure it by hand. So we want to substitute in our values with labels for m and b in our equation. If we read this equation, it tells us the volume of a sample of water in cubic centimeters is equal to 0.9685 cubic centimeters per milliliter times the volume in milliliters plus 0.2908 cubic centimeters. Now if we really stop and think about what it is that this graph represents, we might realize that our y-intercept is throwing off our calculations. The y-intercept is where the line on our graph crosses the y-axis. So in this case, it actually represents the volume in cubic centimeters when we have 0 milliliters. Think about that for a second and decide whether or not that is a logical thing to say. If you have 0 milliliters, you would have an empty container. Is there any way you could possibly have any cubic centimeters if you had 0 milliliters? And what if your intercept was negative? We can't have a negative amount of volume in a container. In lab situations, the y-intercept gives us an indication as to the amount of error in our procedure. Now there is always error. When we measure a volume in milliliters, we are estimating to a certain place value. Just that estimation allows us some error, as someone else might estimate a different value. Also think about when you measured the height of the column of water. Did the end of the ruler represent 0 centimeters? Did you notice that? Were you estimating a value there as well? Were you not estimating to the next unknown place value and rounding your measurements? Not being precise enough in our measurements sometimes makes a big difference in our results. So we know there is always a bit of error associated with our data. What we want to know is whether it is within an acceptable range. For our purposes, we are okay with an error of 5% in either the positive or negative direction. To determine this, we will run a simple analysis on our y-intercept by taking the absolute value of the y-intercept and dividing it by the highest value that we measured in our y variable. We know the y-intercept value from our equation, in this case, a positive 0.2908 cubic centimeters. To find the highest y value, we need to go back to our data. We graphed cubic centimeters on the y-axis, and the highest value that we measured was 23.99 cubic centimeters. Dividing the y-intercept by the y-maximum gives us a value of 0.01212, which converted to a percent gives us 1.212%. This is below our acceptable error of 5%, so we can ignore our y-intercept for this data. Since the y-intercept can be ignored in this case, we want to rewrite the equation to reflect that. To do this, we simply leave off the y-intercept and are left with the volume in cubic centimeters equal to 0.9685 cubic centimeters per milliliter, multiplied by the volume in milliliters. This leaves us with a simple equation that will allow us to plug in either variable in order to determine the other. So with any data that we graph from our lab, the first thing we want to do is write a slope form equation. Start with the y equals mx plus b form, and then substitute in the variables and the values that were used and determined in the experiment. We then want to analyze the y-intercept to see if we can ignore it. If the result of this analysis is under 5%, we can ignore the y-intercept and then rewrite the final equation.